Welcome back. Now let's try to apply our understanding of Kirchoff's current law on this diagram. So this is the same diagram we have been looking at before with 6 elements. So let's first of all label all the nodes. So this is going to be node A. Let's call this node B, node C, node D, and this is going to be another dot. Now the very first step while solving any problem using KCL is that we need to mention all the branch currents along with their directions. And if you don't know the directions of the currents, we can assume any direction. Okay, so here we don't know the directions of these currents, so let's assume that this current through the first element is flowing upwards, and since this subscript is 1, let's call this I1. This is element 2, so let's assume its current is flowing towards right with the name I2. This is element 3, so let's call its current I3. Let's call this current I4 and let's assume it flows towards the right. Then I5 and I6, let's assume both flow downwards and call them I5 and I6 respectively. Now we can write down the equations of KCL for each of the nodes. So let's start with node A, which is the simplest one. So the equation for node A would be, you remember there are 3 different forms of KCL equations. So let's use the first one where we write currents entering the node on one side and currents leaving the node on the other side. So for node A, the current entering this node is I1 and current leaving is I2. Since there are only 2 currents, so on the left side we would have I1, that is the current entering, that is equal to I2, which is the current leaving. For node B, we have 3 currents. So I2 is entering and I3 and I4 both are leaving. So entering current on one side, I2, and the sum of leaving currents on the other side. So I3 plus I4. I3 plus I4. Then for node C, again we have 3 elements. So I4 is entering, I5 and I6 are leaving. So for node C, I4 is entering and I5 and I6 are leaving. So I5 plus I6. And lastly, for node D, you can see that node D has 4 elements connected to that. I3, I3, I5 and I6, all of these are entering this node. I3 plus I5 plus I6 is equal to, and the leaving current is only a single current, which is I1. So that is how we can write the KCL equations for each of the nodes. In this process, finding a current means finding its magnitude as well as its direction. And here we arbitrarily assumed all the directions for currents. If we were given some solid numbers, then we would first do all the calculations, and at the end of the calculations, if the value for a current turns out to be positive, that means our assumed direction for that current was correct. On the other hand, if the value for a current turns out to be negative, then that would mean the current actually flows in the direction opposite to our assumed direction. To rectify that, we would reverse the arrow on the diagram and the value of the current becomes positive. Now let's look at this scenario where for node B, we are given some actual numbers. So again, for node B, the equation was the current entering node, which is I2, that is equal to I3 plus I4. So I2 equals to I3 plus I4, and this is not the equal to sign. We're just writing the equation for node B. Now, since we know the values for I2 and I3, let's put them into this equation. I2 is 5 ampere. 5 ampere is equal to I3, which is 2 amperes. plus I4, which is unknown. Now to solve this equation, we would place I4 on one side and everything else would go on the other side. So 2 amperes goes to the other side and becomes minus 2 amperes. So this implies I4 equals to 5 amperes minus 2 amperes, and that turns out to be 3 amperes. So as we said before, if after the calculations the value for a current turns out to be positive, which in this case is I4, then that means that the original assumed value for the current was correct. So this is 3 amperes, so we can simply write it as 3 amperes. And now if you compare these values, it makes perfect sense because 5 ampere is entering this node, and from here 2 amperes is leaving and here 3 amperes is leaving. So a total of 5 amperes is being divided into 3 amperes and 2 amperes. Now let's look at another scenario where we are still talking about the node B, but in this case the values are a little different. So for node B, again, the equation was I2 equals to I3 plus I4. Now we can put in the values. I2 is 6 ampere. I3 this time is 7 ampere plus I4. Now if we solve for I4, we get 6 ampere minus 7 amperes, which turns out to be minus 1 ampere. So what do we do when the current turns out to be negative? Well, in this case, we can say that minus 1 ampere is flowing towards right. However, it is not very intuitive, so instead we reverse this sign and also we reverse the direction of this current. So instead of writing this, which is not the preferable way, we reverse the direction of current and we write I4 equals to, instead of minus 1, now since we have reversed the direction of current, we would call it plus 1 ampere. So coming out with the negative value for the current means that our original assumption for the direction of current was incorrect, so we have to reverse it. And now if you compare the relative magnitudes of the currents, from this side 6 ampere is entering node B, and from this side 1 ampere is entering node B. So the total current entering is 6 plus 1 amperes, and that is equal to 7 amperes. Now if you look at the leaving current, it is also 7 amperes. So that makes perfect sense. So that is how we can interpret the result of a current calculation if it turns out to be positive or negative. Thanks for watching and see you in the next lesson.